In this segment, I'd like to talk about how we use Booleans, how we create Boolean values, and how we write definitions using Booleans. And I'll also come back to the topic of calculation, how we can by hand evaluate functional programs written in Haskell. Okay, so one of the ways that Booleans get created is by running tests of various kinds. So Haskell has functions to compare integers, so you can see it asks whether one integer is less than another or less than or equal to another, or whether two integers are unequal. And in fact, you can do a similar thing for floating point numbers using the same symbols. So less than tells you whether one float is less than another. Whether one float is less than or equal to another is denoted by less than or equal, and so on. And indeed, equality is a prime example of what's called an overloaded operator. You can use the equality operator to compare two integers to see if they're equal. You can use it to compare two Booleans. You can use it to compare two floats. In fact, you can use it to compare two elements of a type T, as long as that type T has an equality function over it. Now, I don't want to go into the technical details of how that's done using type classes quite yet, but we will come back to that later on in the course. But suffice it to say for the moment is that we have these overloaded operators, and we can also overload functions, so that the same symbol is used for equality over Booleans, over integers, and so on. And the same for inequality, ordering, and so on. So one way that Booleans get created is by these operations. But another thing we can do with Booleans is use them in conditionals. And we saw in an exercise that we looked at earlier on, we looked at a definition of a minimum function which used the if then else operation, the operation which says if x less than y, the answer is x, otherwise it's y. And I asked you what a good definition of the minimum of 3 was. And the way that worked was not to define it from scratch, but it was to say, oh, we could use the minimum function with 2 arguments to give us the minimum of 3. We first find the minimum of x and y, and then the smallest of all 3 is going to be the minimum of that, the minimum of the first 2, and the third. And that indeed gives us the solution we want. Now, we've started to define functions. We've defined min xy there. We've also defined min t xyz. How do those functions get used in calculations? Well, we use these equations in calculations directly. We replace the left-hand side, by the right-hand side. We don't do quite that. We replace an occurrence where you replace the variables on both sides. So for example, we've got the equation min t xyz is min of min xy and z. That, for example, in a calculation will be used as min t of 2, 4 and 1 is replaced by the minimum of 2 and 4 and 1. And in a similar way, unpacking the definition of if then else, if we see an occurrence of if true, then 2, else 4, that gets replaced by 2. And if we see an occurrence of if false, then 2, else 4, that gets replaced by 4. Now let's see how this all works out in practice. Okay, you can see here I've written the definitions of min xy and min t xyz here just to remind us. Now let's work through an example. Let's look at min t of 2, 4 and 1. Okay, by the definition of min t of 2, 4 and 1, that's equal to, and we'll just put it directly underneath, min of min 2 and 4 and 1. So you can see here we've replaced x by 2, y by 4 and z by 1. Now how do we go on and further evaluate that? What we do is we use the definition of min xy. So we have min of if 2 less than 4, then 2 else 4 and 1. And then we can work out the value of 2 less than 4. So that's if true, then 2, else 4. And the second argument to min is 1. And remember that if true, then 2, else 4 is simply 2. So now we're reduced to evaluating min of 2 and 1. Now by the definition of min of 2 and 1, that's if 2 less than 1, then 2, else 1. And that is if false, then 2, else 1, which is 1. So we've got the answer we would have expected for the minimum of 2 and 4 and 1. And we got that, the steps we took in that were by using the equations at the top and replacing the variables in them, x and y, by actual values, and that allowed us to make the calculation work out. We replaced the left-hand side, min xy, by if x less than y, then x else y, with suitable values for x and y. And that's how calculation proceeds in Haskell.